A significant problem in solving the tracing problem is to avoid obstacles, which are already composed objects or communications between them. The big advantage of the voxel approach is the ease of detecting an obstacle by voxel code, 0 or 1. The simplest approach is to ignore obstacles before encountering them. Such an algorithm would look something like this: choose the direction to move toward the target, and move until the target is reached and the direction is free to move. Given that the transverse area of the channel can repeatedly exceed the size of one voxel, it is possible that a valid trace option in this layout situation is not at all. The principle of obstacle avoidance in the construction of voxel method. The known trace algorithms closest to our approach are described in the following. Dijkstra's algorithm. Algorithm A80*. Dijkstra's algorithm. Algorithm A80*. The simplest approach implemented in these algorithms is to ignore obstacles before encountering them. The structure of the choice of direction of movement is determined by the rule to move back to choose a different direction in accordance with the strategy of the traversal. This allows us to argue that these algorithms contain elements of artificial intelligence, AI, since the solution is chosen according to the predicative principle of if, then. In the works of Dijkstra EU, Donald Irvin Knuth, Thomas H. Corman, etc., various obstacle avoidance strategies, heuristics, based on both random search and artificial intelligence algorithms are analyzed. Each of them has both its limitations and areas of preferred application. Examples of different trace algorithms are shown in A. A shows that although the well-known Dijkstra algorithm was able to pave the way from the start to the endpoints, it did not do it rationally, making an extremely many unnecessary movements and repeatedly unnecessarily changing the direction of travel. Examples of tracing when bypassing various obstacles in 2D staging. Voxel algorithm A operates in a more reasonable way, B, and is commonly used to find the optimal shortest path. But this algorithm is not able to take into account the given gap, delta neighborhood, the route may pass too close to the areas of prohibition. Thus, the search for the path of the trace by the algorithm A gives the best results but does not always provide a solution to the problem. In addition, the algorithm A is not able to design trajectories with a given degree of smoothness, since such a task has never been set before. As it was already noted earlier, the strongest side of the algorithm A, which led to its choice by us as a prototype, is the possibility of optimal and heuristic trajectory search. The literature shows that in many cases heuristic search works better than other search strategies. The heuristic function of the algorithm determines the choice of the search direction to the target vertex. If the heuristic function is valid, that is, does not exceed the minimum cost of the graph to the target vertex, then the algorithm A is guaranteed to find the shortest path. The modified algorithm A uses a set of heuristics that provide for multidirectional search. The search for direction is conducted not as usually on 4 and 8 directions, respectively in a plane and space, A and B, and in 8 directions, if the construction of the channel occurs in the plane and 26 adjacent vertices in the design of the spatial channel, C and D. Increasing the directions of the path search in the original and modified algorithms. To implement the proposed trace algorithm, the Advanced Pathfinder System, APS, program was written in Microsoft Visual Studio 2010, using the C# programming language. The solution of the task was carried out within the framework of the dissertation research by Nhi Toon, Republic of the Union of Myanmar, a postgraduate student of mine described in. With this program, you can use the improved algorithm A and find a rational trace between 2 points in 2D and 3D spaces, taking into account the areas of prohibitions. Carry out smoothing of the trace received at the previous stage either on any set radius or on the maximum possible radius with a subsequent check of accomplishment of a condition that the minimum radius is not less than the set Raman. Ensure that the trace passes at the specified minimum distance delta from already placed objects and areas of prohibition. Use the improved algorithm A and find a rational trace between 2 points in 2D and 3D spaces, taking into account the areas of prohibitions. Carry out smoothing of the trace received at the previous stage either on any set radius or on the maximum possible radius with a subsequent check of accomplishment of a condition that the minimum radius is not less than the set Raman. Ensure that the trace passes at the specified minimum distance delta from already placed objects and areas of prohibition. Testing showed significantly higher performance of our modified algorithms than the original one. It should be recognized that the described program, which implements the voxel method of body tracing, is not integrated into any existing CAD system, so the geometric information is entered into the program in parametric form. This reduces the performance of the build process. Integration of this program with any CAD system in the form of a separate built-in calculation module is an actual technical task. When designing the SC, the question on estimation of the effective area of solar panels arises, taking into account their inevitable shading by each other and other structural elements of the spacecraft SC. All this significantly limits the functionality of the SC. When designing SC or ground-mounted solar power plants, we have to decide on the area of solar panels. If there are a small number of panels, then the solar energy absorption will be small, and if there are too many, they will work inefficiently, shading each other, not to mention the additional costs for them and increasing the mass of the entire SC. Therefore, the solution of this question can be considered as an optimization problem of mathematical programming. Partial shading of solar panels in space on the International Space Station, ISS. Voxel geometric models do not require complex formulas or logical constructions for their implementation. However, their practical implementation has its own specific complexity. In addition to the need to convert the initial parametric model specified by the constructor into a receptor model, the complexity is conditioned by the need to take into account the position and value of each voxel, out of many millions in the voxel matrix, as well as to create a mechanism for visualizing the results. The solution of the task was carried out within the framework of the dissertation research by Quy Minh Khan, Republic of the Union of Myanmar, a postgraduate student of mine described in. An essential feature of our approach is that we will not use the classical voxel matrix, filled with 0 and 1, in the calculations, but a multi-digitone, in which additional codes will be added. Specifically, it will be 3-digit, 0, free space, 1, space occupied by the space station residential module, and 2, space occupied of solar panels. Representation of SC by multi-digit voxel matrix. Using a multi-digit voxel geometric model allows you to proceed directly to the calculations of shading. We will move a slice of the voxel matrix with thickness of 1 voxel, A, as a cutting plane along the coordinate plane from the beginning to the end of the voxel matrix, B. Single layer slice of the voxel matrix, A, moving this slice along the voxel matrix, B. In A, it can be seen that on each slice we can put each specific voxel in accordance with either 1, if it coincides with the body of the SC, or 2, if it coincides with solar panels. If there is no match with any elements of the SC, the value of the voxel on the slice remains the initially set value of 0. Looking at a single layer slice of the voxel matrix from the direction of the energy flow WB, we see the layer filled with non-zero code that allows to calculate the total area of space, number 0, the total area of the habitable modules of the SC, number 1, and, most interestingly for us, the total area of solar panels, number 2. Next, everything seems to be simple. Summing up the area of voxel with codes 2 on all sections, we get the area of unshaded zones of solar panels. Single layer slice of the receptor matrix, A, the view of this slice toward the flow, B. In this calculation model, there are situations when along the thickness of the solar panel may be not 1, but several layers of the voxel matrix, for example, 4 layers, resulting in the unreasonable increase of the effective area of solar panels by 4 times. It is also necessary to exclude unreasonable repeat account of already screened objects. To do this, we introduce an additional code 3 in the voxel matrix, which will exclude the account of the areas of the corresponding voxels. The essence of the model change is that once absorbed part of the energy flow should no longer be taken into account. Therefore, starting with some slice of the voxel matrix, everything that follows this slice, the element with the code 2, is forcibly filled with the prohibiting code 3, which does not allow the use of voxels with this code in any calculations.